For decades, Saturn looked like the gentle, dreamy planet of the solar system, the one every kid points to first in a photo because of those impossibly perfect rings. Calm, golden, almost peaceful sitting there nearly a billion miles from the sun. But what the James Webb Space Telescope has actually shown scientists over the past couple of years is the T underneath that serene postcard image. Saturn is running one of the most violent, self-feeding energy machines anywhere in our solar system, a planet where its own north Earnlights are quietly powering hurricane-force winds, which in turn generate electrical currents strong enough to power the northern lights right back again, in an endless, self-sustaining loop that scientists only just finally managed to fully explain. And once you understand what is actually happening up in Saturn's atmosphere, the picture in your head of a calm, ringed world starts to look a lot more like a planet-sized machine that never stops churning. And to understand why this discovery is such a big deal, you have to go back to a mystery that has been sitting unsolved since the early 2000s, because back in 2004, NASA's Cassini spacecraft, which would go on to spend 13 years orbiting Saturn and studying it in incredible detail, made a measurement that genuinely did not make sense. Cassini's instruments suggested that Saturn's rotatio end rate, the speed at which the entire planet spins on its axis, appeared to be gradually changing over time. And if you know anything about how planets work, that should sound deeply strange, because a giant gas planet, like Saturn, with roughly 95 times the mass of Earth, does not just casually speed up or slow down its own rotation over the course of a few years. Planetary spin is not the kind of thing that shifts on short timescales. It is locked in by the physics of how the planet formed and how its mass is distributed. So for scientists to be measuring what looked like a changing rotation rate was, frankly, close to impossible under the normal rules of planetary physics, and that contradiction sat there unresolved for years, nagging at researchers, because there is nothing more frustrating in science than a measurement that keeps giving you an answer that should not be possible. And the reason this mystery was so hard to crack in the first place comes down to how you actually measure the rotation rate of a gas giant. Unlike a rocky planet like Earth or Mars, where you can literally watch a mountain or a crater rotate into view and time exactly how long it takes to come back around, Saturn does not have a solid surface you can track in that way. Its visible cloud tops are made of gas and are constantly shifting and swirling due to weather patterns. So scientists instead have to rely on indirect methods. And one of the most reliable indirect methods involves Saturn's aurora, the shimmering curtains of light near its poles that are essentially a supersized version of the northern lights we see here on Earth. Except Saturn's auroras are driven by its enormous magnetic field interacting with charged particles. And because that magnetic field is generated deep inside the planet and is thought to rotate along with Saturn's deep interior, scientists have long used the timing and behavior of radio signals linked to the aurora as a kind of stand-in clock for the planet's true e-rotation. The logic being that if you can track how that magnetic signal cycles, you can work out how fast the planet underneath is actually spinning. And it was exactly this auroral clock that appeared to be drifting over time, suggesting Saturn's rotation itself was somehow shifting, which is what set off the alarm bells among planetary scientists in the first place. And this is where things started to get interesting. Because in 2021, a research team led by Professor Tom Stallard at Northumbria University in the United Kingdom proposed a genuinely clever alternative explanation. Instead of Saturn's actual physical rotation changing, which, as we already covered, should not really be possible, Stallard's team suggested that Saturn's true spin was staying rock steady the entire time, and what was actually changing was the electrical signal coming from the aurora itself. Their idea was that powerful winds high up in Saturn's upper atmosphere were interfering with the auroral electrical currents, essentially distorting the very signal that scientists were using as their stopwatch. In other words, the planet was not lying to us about its rotation. Our measuring stick was the thing being bent out of shape by winds we did not fully understand yet. And that 2021 study was a major step forward, because it finally explained why the measurements looked so strange. But it also opened up a brand new question that was arguably even more interesting than the original mystery. If winds in Saturn's upper atmosphere were distorting the auroral signal, then what on Earth, or rather what on Saturn, was generating those winds in the first place? And that question sat unanswered for several more years, until the James Webb Space Telescope entered the picture with a level of sensitivity that no previous instrument, including Cassini itself, had ever been able to bring to bear on this specific problem. And this is really the moment where the story shifts from historical mystery to genuinely exciting modern discovery, because Stallard and an international team of researchers from Northumbria University, Boston University, University of Leicester, Aberystwyth University, the University of Reading, Imperial College London, Lancaster University, and Johns Hopkins University's Applied Physics Laboratory turned Webb's infrared eye directly on Saturn's northern auroral region and did something that had simply never been done before. At this level of detail, they observed that region continuously for an entire Saturnian day, watching how temperatures and charged particle densities shifted hour by hour as the planet rotated beneath the auroral zone. And the key to making this work was a molecule called trihydrogen cation, a charged molecule made of 3 hydrogen atoms that forms naturally in Saturn's upper atmosphere and glows in infrared light in a way that directly reflects the local temperature, meaning that by carefully mapping the brightness and behavior of this molecule's glow across the auroral region, the team could essentially build a detailed thermal map of one of the most energetic and turbulent parts of Saturn's entire atmosphere, and the improvement in precision that Webb delivered here was honestly staggering. Previous instruments measuring the same region carried uncertainties of roughly 50 degrees Celsius, which sounds precise until you realize that kind of margin of error completely washes out any subtle temperature variations you might be trying to detect. But James Webb's observations came in about 10 times more precise than that, finally giving researchers the resolution they needed to spot localized patterns of heating and cooling that had simply been invisible to every previous telescope and spacecraft that had ever looked at Saturn. And what they found when they finally had that data in hand was remarkable. The new temperature maps lined up almost perfectly with predictions. From computer models that had actually been built more than a decade earlier, models that had been sitting around waiting for observational data precise enough to actually test them properly. But there was a critical catch buried in those models. They only matched the real data if the source of all that atmospheric heating was located in one very specific place, exactly where the strongest auroral particles come slamming down into Saturn's atmosphere from the surrounding magnetosphere. And when the Webb data confirmed that this was indeed exactly where the heating was concentrated, the entire picture snapped into focus. And what emerged is honestly one of the more dramatic pieces of atmospherics science to come out of the outer solar system in years. Because it turns out that Saturn's aurora is not just a beautiful light show happening passively at the poles, it is an active, ongoing engine that drives huge amounts of energy directly into the planet's atmosphere. And here is where the sustaining, almost terrifyingly elegant cycle comes into play. Energetic charged particles from Saturn's magnetosphere slam into the upper atmosphere near the poles, creating the aurora and depositing a massive amount of energy right into that specific region. As they do, that sudden localized deposit of energy heats the surrounding atmosphere intensely, and because heat naturally wants to spread out and equalize, that intense localized heating generates powerful winds as gas rushes to move from the newly superheated zone toward cooler surrounding regions. And here's the part that makes this a genuine closed loop rather than just a simple cause and effect chain. Those winds, as they move through Saturn's magnetized upper atmosphere, actually generate electrical currents of their own, because moving charged gas through a magnetic field is exactly the recipe physics uses to induce electrical current. And those newly generated currents then feed straight back into the process that powers the aurora in the first place, meaning the whole system essentially recharges itself. The aurora heats the atmosphere. The heated atmosphere produces wind. The wind produces electrical current, and that current helps sustain the very aurora that started the entire chain, over and over again, cycling continuously. And Professor Stallard himself described this discovery using a phrase that captures the scale of what is happening better than almost any other description could, calling it essentially a planetary heat pump, a system where the aurora heats the atmosphere drives winds, the winds produce currents that power the aurora, and the cycle simply feeds itself indefinitely. And when you actually sit with that description for a moment, it is genuinely a little unsettling in the best possible way, because we are talking about a self-perpetuating energy cycle operating continuously across an entire planetary hemisphere, driven by particles slamming in from space, converted into heat, converted into wind, converted into electricity, and converted right back into more aurora, on a world nearly 10 times the diameter of Earth. And if you want a sense of scale for just how violent the wind component of this cycle actually is, you do not even need to look at the aurora specifically, because Saturn's atmosphere, more broadly, is already one of the windiest, most extreme environments in the entire solar system, with equatorial jet streams that have been measured screaming along at speeds up in the range of 1,800 kilometers per hour, more than 4 times faster than the strongest hurricane force winds ever recorded. D on Earth, and that famous hexagon-shaped jet stream sitting at Saturn's North Pole, first spotted by NASA's Voyager spacecraft back in the early 1980s and studied extensively since, is itself an enormous persistent storm system roughly wide enough to fit multiple Earths inside its outline, a 6-sided river of screaming wind that has apparently held that same geometric shape for decades, which is a genuinely strange thing for a fluid system to do, because on Earth our own jet streams wobble and shift constantly, They never lock into a rigid geometric pattern the way Saturn's polar jet stream has, and scientists still do not have a fully complete explanation for exactly why that hexagon holds its shape so stubbornly over such long timescales. And it is precisely this kind of atmosphere, one already known, for extreme winds and bizarre, long-lived storm structures, into which Webb's new discovery about the self-sustaining auroral heat pump now fits, adding an entirely new layer to how energetic and dynamic Saturn's atmosphere really is beneath its calm-looking cloud tops. And this new research did not happen in isolation either, because earlier in 2026, the James Webb Space Telescope and the aging but still remarkably capable Hubble Space Telescope actually teamed up to produce what NASA described as the most comprehensive view of Saturn ever assembled, combining Webb's infrared vision, which can peer down through different layers of cloud and haze to reveal chemical composition and deep atmospheric structure, with Hubble's visible light imaging, which captures the subtle color variations across Saturn's banded cloud tops. Larger feedback loop that helps explain why this entire aurora-driven heat pump system remains so remarkably stable over such long periods of time, rather than fizzling out or spiraling out of control. And Professor Stallard and his colleagues have pointed out that this discovery likely has implications reaching well beyond Saturn itself. Because if a planet's atmospheric conditions really can generate electrical currents that reach all the way out into the surrounding space environment and then loop back to influence the atmosphere again, similar processes could plausibly be happening in the upper atmospheres of other giant planets too, including Jupiter, Uranus, and Neptune, worlds that in some cases are even less well studied than Saturn, and possibly even in the atmospheres of giant exoplanets orbiting distant stars that Webb is already busy examining as part of its broader mission, which means this single piece of Saturn research might end up reshaping how planetary scientists think about atmosphere and magnetosphere interactions across an entire category of worlds throughout the galaxy. And there is something genuinely thrilling, in the truest sense of that word, about realizing that the beautiful ringed planet you might have grown up seeing in textbook photographs is not actually the placid, unchanging world it appears to be from 90 million miles away through a backyard telescope, but is instead a place where charged particles raining down from space collide with the upper atmosphere hard enough to spark light shows visible from Earth, where that collision generates heat intense enough to whip up winds faster than anything you would ever want to stand in, where those winds are themselves powerful enough to generate their own electrical currents, strong enough to feed right back into the very aurora that started the whole process. A closed loop of energy that has apparently been running, quietly and continuously, for as long as anyone has been watching, and possibly for the entire multi-billion-year history of the planet itself. And it took the extraordinary sensitivity of the James Webb Space Telescope, watching patiently for an entire Saturnian day, mapping temperature differences with a precision 10 times sharper than anything that came before it, to finally catch this self-sustaining planetary engine in the act, and prove, once and for all, that this is exactly what has been happening up there this entire time, solving a mystery that had puzzled astronomers for more than 2 decades, and, in the process, revealing that Saturn is a far stranger, far more dynamic, and honestly, in its own quiet way, a genuinely terrifying world than its calm and beautiful rings would ever let on. And if you want to really sit with the scale of what is happening up there, it helps to compare it to something a little more familiar first. Because Earth has auroras too, the northern and southern lights that people travel thousands of miles just to witness dancing overhead in places like Iceland, Norway, or Alaska. And those displays are already spectacular enough to build entire tourism industries around. But Earth's auroras are, relatively speaking, a gentle whisper compared to what is happening at Saturn's poles. Our own aurora is driven by the solar wind, a stream of charged particles from the sun interacting with Earth's comparatively modest magnetic field. And while that process absolutely does generate some heating and some electrical current in our own upper atmosphere, it is nowhere close to powerful enough to create a fully self-sustaining cycle, the way scientists have now confirmed is happening at Saturn. Saturn's magnetic field is dramatically stronger than Earth's, and the planet itself is spinning far faster too, a full rotation in roughly 10.5 hours compared to Earth's 24, which means charged particles get flung around Saturn's magnetosphere with tremendous energy, slamming into the upper atmosphere with a force and a consistency that our own planet simply cannot match. And that difference in raw power is really the reason Saturn's aurora is capable of doing something Earth's cannot, sustaining itself indefinitely through its own feedback loop, rather than needing a constant fresh supply of energy from an external source like the solar wind. And this is part of why planetary scientists get so genuinely excited about a discovery like this one, because it is not just a curiosity about one distant gas giant. It is a demonstration of an entirely different category of atmospheric physics, playing out on a scale we simply do not get to observe anywhere closer to home, and it is worth spending a little more time on the actual detective work involved here too. Because the story of how scientists got from a confusing Cassini measurement in 2004 to a fully solved mystery more than 2 decades later is itself a pretty remarkable example of how slow, careful, patient science actually works in the real world. Cassini spent 13 years orbiting Saturn, from 2004 until its dramatic planned plunge into the planet's atmosphere in 2017. And during that time, it gathered an enormous amount of data on Saturn's magnetic field, its radio emissions, and its auroral activity. But even with all of that data, the instruments Cassini carried simply were not built with the specific sensitivity needed to map fine-scale temperature variations across the auroral region. They were phenomenal for a huge range of other Saturn science, revealing incredible details about the planet's rings, its moons, and its atmosphere more broadly. But this particular puzzle about the rotation rate needed something else entirely. A telescope capable of sitting and staring at one specific region of Saturn's atmosphere continuously for an extended period, with infrared sensitivity precise enough to detect temperature differences far smaller than anything measured before. And that is exactly the gap the James Webb Space Telescope was able to fill once it became operational. Webb was never designed specifically to solve this one mystery. Its primary science goals involve looking at the earliest galaxies in the universe and studying the atmospheres of exoplanets orbiting distant stars. But one of the quietly remarkable things about Webb is just how useful its instruments turn out to be for solar system science too. And the trihydrogen cation molecule that made this whole study possible is itself a fascinating little piece of chemistry worth understanding a bit better. This molecule, often written by scientists using the shorthand H3+, forms when solar ultraviolet radiation and energetic particles ionize hydrogen gas high in a giant planet's atmosphere. And it happens to glow brightly in specific infrared wavelengths that shift depending on the local temperature, which effectively turns it into a natural thermometer written across the sky. Planetary scientists have used H3+ emissions to study Jupiter's atmosphere for years as well, since Jupiter's aurora, while different in its specific mechanics, shares some of the same basic underlying physics, and having a reliable natural marker like this is incredibly valuable, because it means researchers do not have to rely purely on theoretical models. They can point an instrument at the actual glow coming from the planet and read off real temperature data directly. And when the team pointed Webb class, a SNIAR spec instrument, a near-infrared spectrograph built specifically to split incoming light apart into its component wavelengths for detailed analysis, at Saturn's northern auroral region and watched it continuously through a full Saturnian rotation, they were essentially building a movie of how heat moves through that region hour by hour as different parts of the planet rotate underneath the auroral zone. And it is that continuous, high-precision, long-duration observation that made all the difference, allowing the team to finally see the localized heating pattern lining up exactly where those decade-old computer models had predicted it should be if the theory was correct. And when reality and prediction lined up that cleanly, it gave the researchers the confidence to say, definitively, that they had closed the loop on a mystery that had been open since before some of the graduate students working on the project were even born. And there is one more piece of context worth adding here, because Saturn's atmosphere is not just home to this auroral heat engine sitting quietly at the poles. The planet's atmosphere as a whole is one of the most dynamic weather systems anywhere in the solar system, home to storms that can grow large enough to wrap entirely around the planet. The most famous recent example being the enormous storm system nicknamed the Great White Spot that erupts roughly once every Saturnian year, which works out to about every 28 to 30 Earth years. A storm so large and so bright that amateur astronomers with backyard telescopes have spotted it flaring up and dramatically changing the appearance of the entire planet within just a matter of weeks. And Saturn's atmosphere also produces those persistent, ring-shaped storm systems, sometimes referred to as ring spokes, dark or light radial markings that appear temporarily across sections of Saturn's rings themselves, a phenomenon first spotted by Voyager back in the 1980s and studied further by Hubble more recently, believed to be linked to electrostatic charging in the fine icy particles that make up the rings. And when you put all of these pieces together, the record-breaking wind speeds, the geometrically stubborn polar hexagon, the enormous periodic storms that can circle the entire globe, the electrically charged ring spokes, and now this newly confirmed self-sustaining auroral heat, pump cycling energy between the atmosphere and the magnetosphere without ever running down, you start to realize that Saturn deserves a much more dramatic reputation than the one it currently has in most people's minds. This is not simply a pretty planet with rings. It is one of the most electrically and atmospherically violent worlds in the entire solar system. A planet where light itself is being converted into heat, heat into hurricane-force wind, and wind back into electricity in a loop that has apparently been running, undisturbed and self-sufficient, for longer than human civilization has existed. And the fact that it took the James Webb Space Telescope, an instrument built primarily to look outward at the deepest reaches of the observable universe, to finally turn around and solve a 20-year-old mystery sitting right here in our own cosmic backyard is a reminder of just how much more there still is to learn about the worlds we assumed we already understood. And it is also worth pointing out just how much broader context these new Webb and Hubble observations of Saturn sit inside, because this was never a single isolated snapshot. When NASA released the joint Webb and Hubble imagery of Saturn back in March of 2026, the pictures did not just show the planet in isolation. The wider field images captured several of Saturn's many moons in the same frame, including Titan, the largest of them all and the only moon in the solar system with a thick, nitrogen-rich atmosphere of its own, along with smaller icy moons like Dione, Enceladus, Mimas, Janus, and Epimetheus, tiny points of light scattered around the planet that are themselves fascinating worlds in their own. Right. Enceladus in particular has become one of the most exciting targets in the entire solar system in recent years because of the geysers of water vapor and ice erupting from its south pole, believed to be venting out of a hidden subsurface ocean, and separate research published around the same time as this aurora discovery has even suggested that some of that water vapor and material ejected from Enceladus eventually drifts inward and gets absorbed into Saturn's rings and upper atmosphere, meaning Saturn's atmosphere. He is not a fully closed system either. It is constantly receiving small amounts of material raining in from its own moons, adding yet another layer of complexity to a planet that already turns out to be far